It was at this point that John forgot Hooke's law.
If you've ever taken a physics class, you probably know that force is defined as mass times acceleration. This can be used to measure the force applied to a spring, where looking only at the vertical component of the force will allow the usage of gravity to replace acceleration, which is assumed to be 9.81 meters per second squared, and to be the only acceleration acting on the mass. Using this relationship, it can then be said that mass times gravity will also be equal to Hooke's equation, which states that force is equal to K, the spring constant, which has units of newtons per meter, times the displacement of the spring in meters. So mass times gravity is equal to the spring constant times displacement. Therefore, the measured value of gravity should be equal to mass over K times x. In order to verify the calculated value of K, a measured force was exerted on the spring, and the displacement measured. The spring constant should be the same if Hooke's law holds true in this case, and since the equation is linear, graphs of these experiments should display their linear relationship.
This experiment is proving Hooke's law. First, finding the experimental yield by adding an 86-gram weight to the spring, then measuring the displacement of the spring due to the weight with a ruler. Then adding a second weight and completing the same steps. Using the results from both weights will prove that the spring constant K will stay the same even when a force is applied and causes a different displacement. There needs to be a theoretical value of the spring constant K to compare to the experimental. By adding 2 newtons of force to the spring and measuring the displacement gives a theoretical value of the spring constant K. Continuing by doing this step for each spring to find the individual theoretical spring constant of each spring.
Measurements of displacement and mass from the experiment were plugged into an Excel spreadsheet. The force exerted on each spring was calculated using F equals ma, where m is the mass in kilograms of the object attached to the springs, and a is the acceleration due to gravity, approximately equal to 9.81 meters per second squared. It's important to note that although these values shown are positive, the acceleration due to gravity causes a downward force, which means the experimental forces were actually negative. For the purpose of showing the relationship between force and displacement, the absolute values of the forces are displayed. K values were determined experimentally by dividing this force by displacement, as shown in the original equation F equals negative kx. The percent error was calculated using the theoretical values obtained. None of the errors in K values are greater than 1.03%, but these small differences are due to the tolerance of measuring devices and the estimation of gravity being rounded from a more complex number. As shown in the graph, as force, the independent variable, increases, displacement, the dependent variable, increases proportionally. It makes sense that each color of spring had a different length of displacement for the same amount of force because the K value of each spring varied. This is demonstrated by the blue spring having a higher displacement than the green spring over the same amount of force.
Applications for Hooke's law. A commonplace example is the pen. Every time you use a retractable ballpoint pen, you are using Hooke's law. Manufacturers calculate the typical forces users will apply, as well as the standard distance a spring will need to relax in order to retract the ballpoint. With those variables, manufacturers can find the constant K, or the stiffness, that will ensure the pen retracts far enough. Without this law, pen manufacturers would not be able to measure the constant for a large quantity of identical springs, and then be able to know the amount of force required to displace the spring the appropriate amount, as too little force required to displace the spring will result in activating unnecessarily.
This experiment concluded that Hooke's law was proven true because the displacement was directly proportional to the force, showing a linear relationship. The individual springs' constants were found and compared in order to determine the validity of Hooke's law. With so many uses for this theory in our daily life, it's always important to remember its use and not end up like John.
Hooked on a feeling.